Well, welcome everybody. It's an absolute pleasure to have here today Ian AGOL from the University of California at Berkeley, who's chair of the Severo Ochoa lab called AGOL Laboratory. Yeah, so what can I say about Ian? I mean, it's so he solved some of the most important questions in 3D topology, the topology of three manifolds, the tameness conjecture, the virtual hacking conjecture. So AGOL did his thesis in San Diego, yeah, with Friedman. And then he spent 2 years in University of Illinois at Chicago before going to UC Berkeley. And he is a member of the National Academy of Sciences. He's won the Breakthrough Prize and the Oswald Veblen Prize, among many other things. And yeah, it's an absolute pleasure to have you here today, Ian. Thanks very much.
All right, thanks a lot, Javier. I really apologize for missing the talk yesterday. I was a little bit jet lagged, so thanks for coming back today. So yeah, and I thank Javier and Andre and everyone for their hospitality here at the so-called Ian AGOL Laboratory. I'm a little disappointed there wasn't any Bunsen burners or beakers or anything to play around with, but I guess maybe the laboratory is taken in a broader sense. So anyways, so today I want to talk about hyperbolic knots and links. So those of you attending the workshop this week have been learning about hyperbolic groups and three-dimensional manifolds. So this is kind of at the intersection of those, although technically these aren't hyperbolic groups, but relatively hyperbolic. But anyways, they're closely related. So the goal today then is just to discuss a little bit about hyperbolic three-dimensional manifolds, but sticking to knot and link complements for simplicity or for concreteness. And so this topic of hyperbolic geometry is very important in the study of three-dimensional manifolds via the geometrization theorem of Perelman, or in the case we're considering today, was proved by Thurston in the 70s. And so I want to survey a little bit of what's known about hyperbolic links whose complement is small volume. So this is a topic that Thurston sort of asked about earlier on. And so I'll try to describe a little bit about what's known and what we'd like to know. So first I'll say a little bit about three-dimensional topology and then hyperbolic geometry, and then talk about volumes of link complements. So of course topology has its origins in the work of Poincaré, who I think was interested in studying solutions to differential equations, which the space of solutions can be a topological the topological space, and so you can study the solutions by studying the sort of global properties. I believe that's part of the origin. I mean, I think it came out of also maybe complex analysis and other things, but that's so. Anyway, so that's the theory of topology, and so it's codifying the notion of continuity, and identifying properties of a space that are sort of global, that don't change under small perturbation or deformation. So so we consider sort of two spaces to be equivalent if one can be deformed to another one. Anyways, I think most of the people attending the workshop this week are familiar with these concepts. But the classic example is a topologist can't tell a donut from a coffee cup. So I like to say that I drink my coffee with a donut every morning, because I use a coffee cup that looks like looks like that. So, so these two spaces are homeomorphic, and some of you might have seen the picture of the galactic, the black hole at the center of our galaxy. It sort of looks like a donut, although I think that's sort of a figment of the image. But they were giving out free donuts last week at Krispy Kreme to celebrate the imaging of the black hole at the center of the galaxy. This is something that my brother predicted or would be able to view maybe like 20 years ago, but it took him a long time to view that. Anyway, so there's donuts, but what about this coffee cup? Is this coffee cup the same as this donut? Well, if you try to like make this out of modeling clay and deform it around, you might have a problem getting it to look like this over here. So, so why, in what sense is this donut the same as this donut? Well, there's a homeomorphism between them. I can take all the points here continuously over the points here bijectively, or the compact, so that should be enough. But that homeomorphism doesn't extend to the ambient space, is the issue. So they're still intrinsically homeomorphic, but you can't deform this donut into this one without some sort of cutting and gluing, which is not allowed in topology. So we need a donut that's sitting a little differently. So if we take this donut here, then you can deform it into this donut. So so now we've created a donut. Maybe it's more like almost like a pretzel, but anyways, you can now these two are homeomorphic in a way that one can be deformed continuously to the other one inside of 3 dimensions. So how do we see that these two are not deformation equivalent? Well, what you do is you look at the complement of the space. So anyway, so these sort of donuts are referred to as knots, closed loops of string. For a topologist, you want your piece of string that has a knot in it to be closed, because otherwise if the ends are loose, then in theory you can untie it just by sort of pulling the end through. So an unknotted piece of string can always be untied. So topologists always or generally study knots that are closed loops. And so how do we tell that these are deformation equivalent? This is called isotopy. That means that there's a one-parameter family of homeomorphisms in 3-dimensional space that sends this figure over to this figure. Well, you can look at the complement of the knot, so that's what you get when you remove it from space. So one way you can think about this is if I have some donut like here, like an inner tube, if you take an inner tube and you put a little hole in it, you can turn it inside out if you think of it being made out of rubber. I don't know if anyone's ever tried this. So you sort of pull it out, and in a sequence, now you've turned this inside out, and you can kind of tell it because the stripes have changed. Instead of going around the meridian here, they're now going around the longitude. And what's happening here is the point that you poked out of it is sort of going through infinity. If you think of R3 as being S3 with a point removed, or take the Alexandrov compactification, by adding a point at infinity, then this deformation can be done continuously inside of the 3 sphere, but not inside of R3. Inside of R3, there's an inside and an outside if you don't add the puncture there. Anyway, so that's one way to sort of view the complement. So if we take a figure 8 knot and then we take its complement, then we get something that sort of looks like this. So you can imagine maybe having an apple and there's a worm that eats a hole through it that sort of winds around, and you get what's topologists also refer to as like a ball with knotted hole. But this is a way to view the knot complement. And so what we've done is sort of done this inner tube transformation to this knot here, turned it inside out, and we get the knot complement. And so now, if we can distinguish knot complements, then we can distinguish the knots up to deformation or isotopy, because if I deform one knot to another continuously, then it's an ambient deformation and isotopy, so you get a homeomorphism between the corresponding complements. And so this is, any two knots are homeomorphic because they're just homeomorphic to a circle, or if you thicken it up, to a circle across a disk. But this is one way to distinguish knots. And so the goal of knot theory then is to find invariants that distinguish knots up to isotopy. And so one such invariant comes from geometry, and so that's the one I want to talk about today, the volume of a hyperbolic knot. So people may have heard of other invariants of knots. Well, a powerful one is the fundamental group of the knot complement, which is nearly a complete invariant. And then you might have heard of things like the Jones polynomial, or various sort of homology theories. And but we actually know how to solve the knot equivalence problem. This was worked out by Hemian and Waldhausen in the 70s. And then, can everyone hear me okay? And then you also get a solution to the knot problem via the geometrization theorem. So, so why do we study these other invariants? Well, because they might tell you different information about a knot that you don't see via invariants that solve the homeomorphism problem. So there's still a lot to do in knot theory, even if we know how to tell in principle when two knots are equivalent. Does anyone have any questions or comments? So Gordon and Lukey proved that two knots with homeomorphic complements are actually isotopic. Well, or up to, if you keep track of the orientation, then they're actually isotopic. If you don't keep track of the orientation, then it's only up to maybe mirror reflection. So the knot complement is essentially a complete invariant of the knot up to isotopy, if you like. Now, yeah, so I guess this theorem, when I first heard it, I found it a little hard to understand, but in principle, a knot complement might have a different embedding inside of S3, so it's the complement of a different knot. And if you, I think Johan told you about Dane filling this week, so that would correspond to giving different Dane fillings on a fixed knot that give you back S3. And so they proved that there's only one possible Dane filling that gives you S3. If you have the unknot, though, there's infinitely many Dane fillings that give you S3. However, the corresponding knots are all equivalent. Now, for links, though, there are links that have homeomorphic complements. So here's an example of two links whose complements, when you remove them, the complements inside of S3 are homeomorphic. So you can see this by taking one of these loops here, and there's a disk bounding it, and you sort of cut along that disk, put a full twist in, and then glue it back, and then you get back to this link. So there's a way of seeing this sort of intrinsically, that the link complements are homeomorphic, even though the links are not isotopic. So even though the complement's not a complete invariant here, you can add a little extra data about where the meridians are for these links and recover the link up to isotopy in principle. Now, let's go to the second topic now, so hyperbolic geometry. So non-Euclidean geometry was originally discovered by Lobachevsky and Bolyai, and maybe even Gauss. So the original case was in 2 dimensions. So there's a Klein model. You can take a disk and have straight lines in it, and this gives you a model for your non-Euclidean geometry, so it doesn't satisfy the parallel postulate. You have a line here and many non-parallel lines, but it satisfies the other classical axioms of geometry. Or there's a Poincare model where you have a disk and you have geodesics orthogonal to the boundary. Or another model, conformally, you can take a Mobius transformation to send this disk to the upper half plane in the complex plane, if you like. And then geodesics that are orthogonal to the boundary, or maybe vertical lines, give you the shortest distance between points there. What about in 3 dimensions? Oh, here's a sort of model for this using Crochet by Dana Timana. So I'm interested though in 3 dimensions. So one way I like to describe it is if you had a table with a chunk of glass sitting on it, and so that the speed of light in this glass is varying proportional to the height above the table, then you get a geometry here by asking between 2 points, how long does it take for light to get between them? And it turns out that light will take paths that are circles orthogonal to the tabletop. And I'll think of the tabletop as being the complex plane, if you like. And so this includes, in the limit, vertical lines. And so if I go along a vertical line, I get slower and slower as I approach the table, and it takes infinite time. So this table is actually infinitely far away because it slows down. So in principle, you can make some sort of medium that had this kind of property, a kind of glass with varying index of refraction or varying speed of light. And it'd be cool to see something like this in physically made, if possible. Another thing, so this is some sort of physical approximation to upper half space. And I think people in the workshop will learn more about hyperbolic manifolds in the coming week from Bruno Martelli's course. But anyways, this gives some sort of physical approximation to upper half space. Another thing that I've learned recently is that there's a sort of approximation to hyperbolic geometry in the ocean, I guess, that in a certain range in the ocean, the speed of sound varies linearly. And so if you look at sound waves flowing through the ocean, you would expect them, again, in a certain range to follow circles that are orthogonal to the surface of the water. So this is sort of the upper half space model, but flipped upside down. And again, this is only just approximation in a certain regime, and I actually don't know if this has been sort of experimentally verified. But whales or dolphins communicating, the sound waves might actually have to go deeper in the ocean where they can move faster and then come back up again to get the quickest between 2 different animals, for example. But this is just it's just an analogy, I think. In a certain range, the things actually flip, and the speed of sound becomes faster near the surface. So now let's talk about hyperbolic manifolds. So the orientation preserving isometry group of hyperbolic free space, it turns out, is isomorphic to PSL2C. And the action of this group on the projective line, so CP1 is the complex plane with a point off at infinity. And the Mobius transformation, so if you've had some complex analysis, you may have seen Mobius transformations acting on the complex projective line. So if I have a 2x2 matrix, say with determinant 1, then it acts on the complex line by AZ plus B over CZ plus D. Now, if I multiply by -1, then the -1s cancel, and so that's why it's PSL2C rather than SL2C, because you mod out by plus or minus the identity, which act trivially. So if we take a discrete subgroup of PSL2C, here I'll call it gamma, then, and without any elements of finite order, so discrete means that you have this, so it's a subset of PSL2C, these 2 by 2 matrices, and discrete means that they don't accumulate at the identity, the diagonal identity matrix. So if you have such a group, then you take H3 and you mod out, you quotient by the action of the group. So you look at all the orbits of these points. So you can think of a hyperbolic manifold as a collection of orbits of points in hyperbolic space that are equivalent under this group action. And that's actually, if you lived in a hyperbolic manifold, that's how it would look to you. You wouldn't think about this compact thing. You would see all these other copies of yourself, and we'll see this a little bit later. So then, the quotient space, if you're familiar with any Riemannian geometry, then it admits a complete constant -1 sectional curvature metric, and that turns out it's equivalent to being a hyperbolic manifold, in this case, 3 dimensions. So anyway, so that's a quick description of. I haven't described how this action works, but you can actually define this extension via quaternions. Or there's other nice formulas for it. Is there any questions on this? So I'll give an example in a second. Or any other questions or comments? Okay, so let's talk now about knot complements. So Thurston, so I mentioned the geometrization theorem. So Thurston showed in the 1970s that most knot complements, in some sense, admit a hyperbolic metric. This was originally, the first examples were due to Robert Riley and Charles Jorgensen, who both discovered that there's a hyperbolic structure on the figure 8 knot complement. But Thurston showed that, in his after work of Jacob, Scheel, and Johansson, that there's a kind of trichotomy for knots, that there's torus knots, and so this is a knot that sits on the surface of an unknotted donut. That's one kind of knot. There's a connect sums, where you have a knot here, like the trefoil knot connects sum with the figure 8 knot. And more generally, what's called a satellite knot. So I can take a knot, and I can then insert another knot that winds around it, sort of like a satellite orbiting around this other knot. And if you do that right, then you can get a more complicated knot. So otherwise, if you're not a torus knot, or you're not you can think of a connect sum as a satellite. Either knot is orbiting around the other one. You just inserted a little knot somewhere. So if you're not a torus knot and not a satellite knot, then Thurston showed that the knot is hyperbolic. Its complement admits a complete hyperbolic metric of finite volume. So let's look at the example of the figure 8 knot complement. So here we have some 2 by 2 matrices, and so these two matrices can be represented by loops. I think of taking a point, and those little arrows are indicating there's a loop that goes underneath the knot and back to your base point. So if you're familiar with the fundamental group, then this is describing two generators of the fundamental group. And so this generates the discrete group, which when you quotient H3 by it, you get something homeomorphic to the figure 8 knot complement. So this is a 6th root of unity here. And so the matrices will have entries lying in this number field, Q adjoin the square root of -3. In fact, in the ring of integers of that number field. Now, a manifold then has there's a notion of volume. So you integrate 1 over z cubed over a region where z is the vertical component above our table, our sphere at infinity, C. So for the figure 8 knot complement, it turns out that we have over here, it turns out you can get it from some region in upper half space where there's these tetrahedra. This goes infinitely far up, continues up, and there's these two what are called ideal tetrahedra, and you glue up these faces together as indicated. So B gets glued to B prime, C gets glued to some C prime down here, and A prime gets glued to this face A down here. So if you and it turns out there's a unique way to glue these things together by an isometry, and these are these gluings will correspond to products of these matrices here. So you apply one transformation, and it'll take B over to B prime, C to C prime, and A to A prime. And when you make these identifications, then you get a quotient topology, which is homeomorphic to the figure 8 knot complement. So this is what's called a fundamental domain for the group action. It's a set of points that every orbit of that group can be taken into this region. So it's and also that the part that's replicated, so like B and B prime is replicated, but it has measure 0, so it doesn't contribute. So you can now integrate 1 over z cubed over this region and get the volume of the quotient space, and it turns out it's well defined. It didn't depend on which fundamental domain we chose. And this integral will be finite because when you integrate 1 over z cubed from z to infinity over some compact region, you get some finite number. So in this case, the hyperbolic volume is some number 2.0298, which has this expression. This is a certain value of a zeta function of the field q adjoint square root of -3. And you see this, it's 1 over 1 squared plus 1 over 2 squared minus 1 over 4 squared minus 1 over 5 squared. So it repeats with period 6. And it's omitting all the numbers divisible by 3, but then the signs alternate. Yeah, question? Do you have just this unique hyperbolic structure? Is that why this is the only possible volume? Yeah, good question. Yeah, the question is, do you have a unique hyperbolic structure? Yes. So, so that's a theorem of Mostow that if you have a complete hyperbolic metric of finite volume, then it's unique up to isometry, and actually up to isotopy as well. It becomes that's why it becomes a topological invariant. Good. Are there any other questions? Yeah. Oh yeah, good question. Yeah, so I've been a little careless here, but where is the knot in this picture on the right here? Well, it's sort of off at infinity. So really, this is the homeomorphic to the interior of this region. So you have this compact manifold with torus boundary. You strip the torus boundary off, and then you get something non-compact. And you what's happening is the knot is sort of getting pulled like taffy off to infinity. So it's infinitely far away, but the volume of that region is bounded and finite. Yeah, good question. Yeah. Yeah, good question. Yeah, so here the distance in hyperbolic space varies like, the speed of light, as I was saying, is like 1 over, is the distance to the table. So if you think of that as a vector, then the vector has to get scaled by 1 over that height to get the length of that vector. And so the length of vectors in this Riemannian metric vary like 1 over, there's a Euclidean metric, and then you scale it by 1 over the height to get the metric in Riemannian, in the hyperbolic space. So that's why it's 1 over z cubed, is because there's, it's 3-dimensional, so you take the vector and you scale it by 1 over the height. Yeah, thanks. And it turns out that this integral is, this volume is invariant under, well, it's sort of clear it's invariant under translations, but it's also invariant under other isometries. So that's something that has to be checked. Any other questions? So Thurston's theorem is much more general. I'm not going to state the general version, but it applies to links as well. A link is just a collection of closed loops. And so here's some examples of links with hyperbolic complements. There's the Whitehead link and the Bromian rings. So like I was just saying, the theorem of Mostow implies that the hyperbolic metric, if it exists, is unique. And so, again, unique up to isometry or up to isotopy. So if I have a hyperbolic metric on a space, I can push it forward by a diffeomorphism and get another hyperbolic metric, but those are isometric to each other. This is in general relativity, this is called the problem of general covariance or something. But here, it's unique up to that sort of equivalence relation. So this becomes an invariant of the link complement, and let me say some class of discrete groups. A way to get a lot of discrete groups is a classical construction of Borel and Harish-Chandra called arithmetic groups, which turn out to be important in arithmetic, as you might imagine, or number theory. So we can take the ring of integers of a quadratic imaginary number field. Now, I don't necessarily expect everyone to understand or to know much number theory, but here, quadratic imaginary number theory is Q adjoint a square root of a negative integer, D, which you can take D to be square free if you like. And then you take PSL2 with entries that are in this ring of integers, in O sub D in this notation. And the 2x2 matrices with these quadratic imaginary integral entries, and whose determinant is equal to 1. And this gives you a discrete subgroup of PSL2C. Well, the quadratic imaginary numbers are, so in general, they'll look like Z adjoint square root of minus D, or or Z adjoint, you can take minus D, square root of minus D over 2. This will be the ring of integers where capital D is called the discriminant. It's either D if it's congruent to 3 mod 4, and otherwise it's 4 times D. So this is just in this second case, these will actually, the 2 will cancel with the 2 coming from the square root of 4 here. So anyways, this is, if you're, an example is like the Gaussian integer, Z adjoint I. And that's a lattice in the plane. It's a discrete subset of the plane. So when you take matrices whose entries are discrete in C, then they're discrete in PSL2C, because they can't accumulate an identity because they're discrete in each coordinate. So this is a way to generate discrete groups, is by this number theoretic construction. And so these are called Bianchi groups, going back to the 19th century. And it turns out these account for all arithmetic hyperbolic 3 manifolds that have cusps. Turns out they're essentially one of these Bianchi groups, up to taking fine index subgroups. So, so this is a big source of discrete groups, and you also have nice formulas for these, called the Humbert volume formula in this case, where you can relate the volume to a zeta function of the number field, and it also has some expression, some number theory expression, where you have this Kronecker symbol. This is a symbol that will be periodic of some period depending on D. And that's, we saw an example of this for the figure 8 knot complement already, which is arithmetic. Turns out that the figure 8 knot complement is the only arithmetic knot complement. That was proved by Alan Reed. Any questions on this? So this is a very quick crash course in discrete groups. And also I should say that by taking finite index subgroups, you can find discrete groups that are torsion-free, and hence you get manifolds. If there's some torsion in these groups, then you have to work more generally with what are called orbifolds. So, okay, any questions on that, or, yeah?
What breaks if you take higher degree number fields?
Right, so what breaks if you take higher degree number fields is that the ring of integers inside of C will not be discrete anymore. So it's only quadratic imaginary. There's other arithmetic constructions associated to these other number fields, but you can get compact manifolds. But yeah, the construction is slightly more complicated. Any other questions? Yeah, good question. Now, for general hyperbolic three manifolds, the volume can be computed sort of algorithmically in terms of dilogarithm functions, or there's various methods for doing this. And there's a computer program that computes hyperbolic structures, and so you can explore the volumes. So Jeff Weeks, who was a student of Bill Thurston, and he got help from many different people. He developed a program called SnapP to compute hyperbolic metrics. So there's some successors to this program called Snap and SnapPy, Pi for Python. So these are give you other abilities. So Snap can do like arithmetic computations, and SnapPy is sort of the SnapP unfortunately hasn't been supported, and it's on an old version of Mac operating system. So you can't run it anymore, except maybe on an emulator. But SnapPy is incorporated into Python. And so these have been an extremely useful tool for studying hyperbolic three manifolds and studying the homeomorphism problem. And these give you really practical ways of telling if two knots are equivalent or not. So SnapPy, it's not guaranteed to work, but it works in practice very well. So here's an image, and I'll show you, I'll demonstrate it in a second if I have time. Let's see. So what would it look like to be inside a hyperbolic space? So this is, actually maybe I'll go to SnapPy right now, so we'll have a look at that. So here's the symbol, a Python that's wrapped around a SnapP that was the original symbol for SnapP. So here's the SnapPy is in you get a Python shell, and then I've already input some manifolds in here, some links. So here's a three-component link. And here's another one. Does anyone recognize this one? Yeah, bromine rings, yeah. I guess the screen is shifted a little bit. And then here's the figure eight. So, whoops. So what you can do is you can draw a picture of these. So let me, maybe I'll show you how that works. So I can draw the knot on the screen, and then so there's which knot is that? That's the unknot, yeah. But I can make it alternating, and now I have the figure eight knot. And you can also reflect it if you want. The figure eight knot's amphichiral, so that's also the figure eight knot. There's only one of them. And then I can send it to SnapPy. And so this is going to give me a new triangulation. So now, I called this one 8 earlier, so I was, now I can browse the figure eight knot complement, the link I just input, and it'll tell me some information about it. So it tells me, whoops, I'm having a little trouble with the screen here, but. So The volume is 2.0298, like we saw before. The Chern-Simons invariant is 0. This is just some exponential minus 16 is 0. The first homology is Z. It also found this manifold in its census. It has various lists of manifolds that you can compare a given manifold to and see where it is. And here's the fundamental group. It has 2 generators and 1 relator. So now I can look at some other aspects of it. And you can also do Dane filling here, but I'm not gonna do that now. Let's look at its Dirichlet domain. So the figure 8 knot, we made it out of these 2 tetrahedra, these ideal tetrahedra. And you can see the 2 tetrahedra here. There's one sort of in the middle of this thing, and then there's 4 corners of the other one. I don't know if you can see that, but now you glue the faces together. The purple faces get glued, and the different colored faces get glued together. And when you form that quotient, you'll get the figure 8 knot. So this is a different fundamental domain. I can also look at this in the Poincare model now, where geodesics are orthogonal to the boundary. So these are viewing hyperbolic space through Euclidean eyes. And I can look at it from the upper half space model. Here's a cluttered diagram, but here the knot is actually off at infinity, and so there's some neighborhood of that's what's called a horoball. And what you have here are pictures of the different horoballs. So there's this pattern of these balls that's preserved by the group. And in fact, the symmetry group of this is one of these Bianchi groups. I can shrink the balls, or I can flip it over. So now we see them. Now we're looking from below the table, and we see all these orbits, and you could even take more of them. Now let's look inside of the manifold. So this is my former student, Matthias Gerner, who works at Pixar. He helps maintain SnapPy. Let's shrink our cusps a little bit. So you can use this to navigate through hyperbolic space. This is an implementation of the GeomView program. And so here, these lines are the skeleton of this triangulation, and the knot, in some sense, is sitting off at infinity. And so this whole pattern here, essentially uniquely determines the knot. We can also look at the symmetry group. The symmetry group is D4, and actually it knows which knot it is as well. So we can look at some of these other guys too. So I think I already have them in here. So we'll browse. Let's see, I think this is the Borromean rings, yeah. We can look at it. So this is the Borromean rings, and I can look at its cusp space. Anyways, this is kind of fun to play around with if you download it. And it tells you a lot of information about the knot and link complements. So anyways, so is there any questions or comments on this? Or?
The navigation view, what the thing is like, they're not copies. This thing is not compact.
Yeah, it's not compact. Yeah, that's why you see these things going off to infinity. Yeah, I have an old computer, so it takes a little while to render this, but if you have a faster computer, it'll probably look a little better. All right, so let's go back to my slides. So that's what it looks like in hyperbolic space. You're actually you're seeing the universal cover in some sense of the manifold, and not the manifold itself. So you would see a bunch of different copies of yourself. In that view there were some balls that were different orbits of a point. Now there's a nice video called Knot Knot that visualizes this sort of thing. So the volume, the Whitehead link complement is 7.3277. That's another one of these zeta functions, zeta the Gauss the Gaussian integers, and you have this alternating sum of 1 over odd numbers squared. This is 8 times g, where your g is known as Catalan's constant. And it's not known if this constant is irrational. Turns out that Frank Caligari showed that that this series converges over the two adics, and it's irrational in the two adics. But I don't know if that has any geometric meaning. So the volume's a pretty powerful invariant of links, hyperbolic links. Thurston and Jorgensen showed that any given volume, there's only finite many link complements with that fixed volume. So here's an example of the Whitehead link and the minus 238 pretzel link. These two manifolds have the same volume. And then with the caveat that there can be infinitely many links that have the homeomorphic complements. But here I'm really talking about link complements. Now, here's another picture. So sometimes links have the same volume, but you might be able to distinguish them by some of these patterns that we saw in SnapPy. So here, these two manifolds of the same volume, you'll see a different pattern of these horoballs in this picture, and hence they're not the same link. And that might not be quite enough to generate, but it's pretty good test. So also volumes are well ordered. That means that any decreasing sequence of volumes will be finite. And they're of order type omega to the omega if you're familiar with ordinal arithmetic. But I'll show an example later. So like for the twist knots, this is an image from Thurston's notes. We had the figure 8 knot, and you can put extra twists in it, and you get a sequence of knots where the volume increases to 3.16, 3.42, 3.55, all the way up to 3.66. Again, this is 4 times Catalan's constant, the Whitehead link. And so what you're doing is you're taking the Whitehead link and you're Dane filling along this second component here with a certain slope, and this effectively adds twists and gives you a sequence of knots. So as you increase the number of twists, the volume will approach that of the volume of the Whitehead link, and so it's increasing, but you can have infinite increasing sequences, but only finite decreasing sequences. Any questions or comments? Now, Thurston asked, he had a survey paper in 1982 describing his sort of theory, and he asked to a bunch of questions, but one of these questions was develop a computer program, and that's what this SnapPy program was developed by Jeff Weeks. And then another question was to tabulate volumes of hyperbolic manifolds and try to get a feel for what knots in the knot table of small volume look like. And so that's something that we're still in some sense pursuing. Now, for example, Champa-Nurkar and Kaufman and Mullen, they made some tables. I didn't write down the volumes, but these are some of the smallest volume knots that they found in the knot tables. And you'll see here that they can look more complicated than sort of classical knots in terms of crossing number. So volume and crossing number are not super well correlated, and that's because you can add these sort of big twists that don't increase the volume a lot, but they can increase the crossing number a lot heuristically. So anyway, so that's sort of experimentally what the smallest volume knots look like. We have the figure 8 knot here. And anyway, so that's, so there's been a lot of work to trying to find the smallest volume hyperbolic links with different number of components. And so this is sort of addressing Thurston's question 22 kind of rigorously. So let me describe what's known. So Sal and Meyerhoff in 2001, they showed that the figure 8 knot is the smallest volume hyperbolic knot. Actually, so there's another manifold that has the same volume called the figure 8 sibling, but it's not a knot complement, so I just didn't draw it here. But you can obtain it by a Dane filling on the Whitehead link. And then in 2009, Gabay, Meyerhoff, and Milley proved that the 5-2 knot is the second smallest volume knot with volume 2.828. And there's another one that has the same volume. That was in the table we saw here. These two knots have the same volume. And then in 2010, I showed that the Whitehead link is the smallest volume manifold two-component link, or the -238 pretzel has the same volume. That's why I showed those earlier. And again, there's infinitely many links with the same homeomorphic complement. So really I'm talking about link complements here. And Yoshida showed in 2012 that, that these two links are, this is really one, that have homeomorphic complements. So there's one 4-cusp manifold which achieves the minimum volume among 4 component hyperbolic links. So the proof of these first two theorems are computer-aided. The proof of the other two theorems uses Perelman's proof of the geometrization theorem, and a result of myself and Storm and Thurston from 2007, which uses minimal surfaces and Ricci flow to estimate volumes when you cut along a minimal surface. So what about 3 components, though? We skipped over 3 here, and so that's what I've been thinking about with one of my students, or he graduated a couple years ago. But so what's the smallest volume hyperbolic link with 3 components? So conjecturally, it's the 3-chain link. This is another one of these things with commensurate with the Bianchi groups. And this is also a mystery. It turns out that all these small volume guys come from arithmetic examples, and we don't really know why that is. That probably doesn't persist, but so this is a subgroup of PSL207. So Q adjoins square root of -7, the ring of integers there. And so this is one that I showed in SNAP earlier. Maybe at the end I'll go back to that. So my student Yue Zhang made some progress on this. He showed that either if you have a 3-cusp hyperbolic manifold, the volume is at least 5.49, which is bigger than 5.33, or there's what's called a suture manifold sitting inside of there. There's a certain kind of submanifold that has a particular property. And we conjecture that the smallest volume of such manifolds is 5.33, which is exactly the volume of the 3-chain link. So we've made a lot of progress on this, but we haven't quite ruled out some technical cases. But these submanifolds, it turns out they have a hyperbolic metric now with totally geodesic boundary. And so you can, we expect that it should be easier to analyze the volumes of such manifolds. There's sort of more to get your hands on when you have a manifold boundary in some sense. So there's various sorts of packing estimates you can make and things that make it more plausible. So this is what we conjecture the minimal volume suture manifold is. So there's a metric here where the blue and the red disks here, they're thrice punctured spheres, they're totally geodesic. And now these yellow 2 components here are sort of off at infinity. So these are what are called cusps, but they're, it's sort of a relative version of the cusps that we saw for hyperbolic knot complements. So this suture manifold, again, is associated with a discrete subgroup of PSL2C that's infinite co-volume, but if you chop off these geodesic half spaces bounded by these circles in the upper half space model, then you'll get this thing here. So anyway, so I feel like we're getting close to maybe solving this 3-component case. But the thing is, we're trying to do it without using computation. So there's a lot of Gabai and his collaborators have used sort of computer-aided proofs where they're analyzing certain moduli spaces and showing that certain things hold over these moduli spaces. So here's a sort of summary of the volume spectrum. So we have the figure 8 knot, 2.0298, the twist knot, and then we don't know what these other ones are. And these accumulate on 3.66. That's this picture of the Whitehead link that's 2 cusps, or the -238 pretzel link. And then these, we conjecture they accumulate on 5.33 and then up to 7.27. That's the four component link. And so we'd like to know what all these other order limit points are. So this is sort of a visualization of the ordering of omega to the omega. So you have discrete set of points that it can accumulate on a point, and then those can accumulate iteratively on a second order accumulation point. So this is an accumulation point of accumulation points. So this one corresponds to omega, this one corresponds to omega squared, omega cubed, and then you go off to omega to infinity, or omega to the omega is the order type of these volumes. And so it's going to be impossible to identify all these things, but that's sort of the goal, to find the small structure. Yeah, question, yeah.
Is 7.27 conjectured, or?
No, that one is, that's Yoshida's theorem. This is the four-component link. Yeah, thanks. And then there's a corresponding diagram for closed manifolds too, but for simplicity, I just wanted to talk about not-in-link complements today. And it's actually just a coincidence that the smallest volume cusp manifolds happen to be not-in-link complements, or they have the same volume as some. So some open questions then. In principle, we can compute the volume spectrum up to any point with some caveats that we don't know how to eliminate repeats. There might be two manifolds that have the same volume, but we don't know how to tell they have the same volume. There's a deep conjecture, number theory, Ramakrishnan conjecture, that would imply that two manifolds have the same volume if and only if they're what are called scissors congruent. So you can cut one of them up into polyhedra and reassemble those to make the other manifold, maybe with mirror reflection. And that's conjectured to the two manifolds that have the same volume, they are equivalent by this cutting and pasting procedure, which preserves volume. And all these examples I showed are of this type. But this is this is a very difficult problem. So we don't even know that the Bianchi groups are linearly independent over Q. That would follow from this conjecture. All right, so if you want some references, the Knot book by Colin Adams is a nice overview of this topic, and then I encourage you to watch the Knot video, which you can find on YouTube. And then Thurston's book, Three-Dimensional Geometry and Topology, gives sort of an introduction to these subjects. So, and I'll stop there, thanks.
It's being recorded, so that's why I'm wanting this up.
This question about the minimal volume of link complements, what makes 3 components harder than 4?
Yeah, good question. Yeah, what makes 3 components harder than 4? It's somehow that, okay, so yeah, so I'll try to say something about that. So let me go back to my slides. So the Whitehead link, you can cut along, there's a sort of obvious disk here that has 2 punctures in it, and it's totally geodesic, and you cut along that, you get a manifold boundary. Now, there's a theorem of Miyamoto that says that manifold achieves the highest volume, the smallest volume compared to the area of the boundary. So what's making the 3-component case more difficult is that this manifold here does not achieve that minimal volume estimate. 5.33 is bigger than the 3.66, which would be the minimum volume, and that's sort of what's making this harder. But we're trying to use other techniques to approach it. Use Yue Zhang's thesis used what's called Thurston norm, and understanding in detail the Thurston norm of such a manifold and various properties about it. But yeah, that's essentially where so there's certain packing estimates of Miyamoto that says that for a given Euler characteristic of a manifold, there's some minimum volume that can be achieved, and that's where the sort of bottleneck is. Yeah.
So in that table with the minimal volumes that you just showed, so I believe that for the 4 components case, it is exactly the double of what you got in the 2 components case. So is this a fluke? So I could imagine that it is a double cover, the 4 component link of the Whitehead link. Is that right?
Yeah, good question. Yeah, so this link here, like you're saying, its volume is twice that. Yeah, so that's they're actually both commensurable with PSL2 Z adjoint I, the Gaussian integers, and so they're maybe it is. Let's see. I'm not certain it's actually a double cover, but they're related. They both have finite index subgroups or finite sheet of covers that are isometric, and hence you get this volumes are proportional to each other or by this factor of 2. Yeah, good question. Yeah, that's I should have mentioned that. So these 2 are arithmetic over the Gaussian integers. This one is not arithmetic, but the figure 8 knot is, and then this other one is 3-chain link is arithmetic as well.
Okay, so, and if I may ask just one more question. So you mentioned the example of the twist knots where in some sense we get a limit and we get a link. So to me, this is strikingly reminiscent of what happens in the case of surfaces whereby train tracks we convert to a lamination or maybe a disjoint union of curves. So I guess my question is there some analogous theory of train tracks for links, carrying or?
Okay. So train tracks for links. Well, yeah. So the way that these are similar is they're both sort of Hausdorff limits of the sequence. So, but yeah. So you can associate various 3-dimensional versions of train tracks to knots and links, what are called laminations. So it's a 3-dimensional version of a train track, and for knots, for fibered knots, there's a canonical sort of lamination associated to it. So like for the figure 8 knot, there's a canonical lamination. Gabai's proved that any knot complement has some sort of lamination, but it's not necessarily canonical if it's not fibered. But there is sort of a 3-dimensional version of train tracks. Yeah, good question. Yeah.
Thank you.
Thanks for the talk. I have 2 questions. If I give you a knot or a link, how do you tell whether it's hyperbolic? And then how do you tell whether it's arithmetic or not? And then the other question is, what's the deal with the zeta functions? Where are they
Right.
coming
Yeah.
from?
Okay. Let's see. So the first question, so I could put a knot into SnapPy. So let me go to my shell here. And and I can let's say whoops. I didn't capitalize it. Oops. Or actually, let's do trefoil. So let's draw the trefoil knot. So that's the unknot. I make it alternating. I get the trefoil, and then I can send it to SnapPy. And now I can browse the trefoil knot. And it shows, well, the volume is 0. So this is not a hyperbolic knot. It's a torus knot. And, H1Z, but you have the fundamental group here. So there's an algorithm that to find a hyperbolic structure where one way is to do it is you look for representations into PSL2C, and then you try to find a representation that's discrete and faithful, and that's one way to do it. And so here it's failed to do that. So it's taken this presentation, the fundamental group, you put 2 matrices inside of there, and then this relation here tells you some relations that those matrices have to have. And so here it hasn't found, well, actually there are matrices that satisfy that, but they'll be in PSL2R. And you get representations, but they're not discrete or of finite covolume. So that's one way to do it is via representations. I mean, it's a little more complicated than that, but that's sort of the idea. And then the other question was, right, oh yeah, how do you tell if they're arithmetic? Yeah, so to test something as arithmetic, you can, there's also algorithms to do that. The traces will be, well, if it's cusp, they would have to be these quadratic imaginary integers. And there's some data that you can use to test this. Is what's called a quaternion algebra, and there's some other things and it's actually will tell you if the thing is arithmetic. So you can compute this data. So if you'd like to learn about that, there's a good book called The Arithmetic of Hyperbolic Three Manifolds by McLaughlin and Reed that discusses these invariants that detect whether something's arithmetic. And then the zeta functions appear. Let's see, what's a good succinct reason for that? There's it sort of comes from lattice point counting. So you can think of trying to count lattice points in PSL2C. And if you do the count the right way, then you end up getting one of these zeta functions. But that's, maybe I can't say much more than that without a little more discussion. So, but I'd be happy to talk more about that after, yeah.
So is it known that omega to the k in the order of volumes corresponds to like k component lengths?
Right, yeah, I guess or k plus 1 in this case, because we're just looking at knots and links. If you look at the closed manifolds, then it would be k cusps. That's right, yeah, so that follows from Thurston's and Jorgensen's theory. So basically, when you have a limit, what's happening is there's some geodesics in the manifold in this sequence of manifolds which are converging to zero, and the manifold sort of limiting is something with this cusp. And so each time you have a limit point, you're sort of drilling out a curve from the sequence of manifolds to get the limiting manifold. So and then conversely, if you have n cusps, then you can Dane fill each cusp individually and get a sequence of hyperbolic manifolds that converge to that. So that follows from Jorgensen and Thurston's theory, yeah. For the proof of that, you can look at, well, Thurston's notes, which can be a little hard going, but I recommend looking at Thurston's notes from his Princeton lectures. Or you can look at, there's a book of Benedetti and Petronio that discusses the Dane surgery theorem, and there's Ratcliffe's book on hyperbolic manifolds that discusses these theorems. Yeah, so that follows from, essentially from the Dane surgery theorem. Yeah, so while you're bringing the microphone, yeah, so you can deform the representation a little bit, and the representation might not be discrete anymore, but sometimes it can be discrete, and that's when you get a hyperbolic Dane filling, but you've changed the topology of that quotient. The representation is no longer faithful. You've killed something that corresponds to filling in a certain meridian. That meridian gets killed. And so that's how this Dane filling theorem is proved.
Do we know how representative are the arithmetic manifolds? Like, what's the probability of a manifold being arithmetic?
Right, yeah, good question. Yeah, the arithmetic ones are very sparse. So they're, in fact, their volumes are actually discrete. So if you have a sequence of manifolds whose volumes converging to something, then most of those are not going to be arithmetic. So yeah, it's kind of weird that they're very sparse among the collection of all manifolds because the volumes are discrete. They have these nice arithmetic formulas for them as well, these generalized zeta functions, but and yet they show up a lot when we look at small volume things. So all the smallest volume, or most of the smallest volume things we've found in like the smallest volume closed manifold is the Weeks manifold, and that's an arithmetic manifold. So for some reason they seem to appear when you look at small volume things, and we don't really understand why.
Okay, well, if there are no other questions, let's thank Ian AGOL again.
All right, thanks.